Section 3.9 is derivatives of logarithmic and exponential functions. And we've already talked about the derivative for just our basic e to the x, and then also applied some chain rules for e to the x. But we're going to talk just a little bit more about what it looks like if the base is not e, but then also logs here in this section. So what we've seen so far with e is that the derivative for just our most basic e to the x function is e to the x. The derivative with respect to x for e to the x is e to the x. And if there's anything else in that exponent besides just a plain old simple linear x, then we would have to apply the chain rule. So if we were asked for the derivative of e to the f of x, so that exponent could be any function of x. Remember, the derivative for e always contains itself, but then we would also have to multiply by the derivative of the exponent. And that's just the chain rule. That's what the chain rule says we have to do. So we would also say times f prime of x. And we've already worked with that a little bit so far, but I'm reminding you of that because we're going to have the same type of rule when we deal with logs. We're going to have a basic rule for logs, and then we're going to have a chain rule for logs. And then once we learn these rules for logs, we need to go back and remember all of our other rules, our power rule, our product rule, our quotient rule, and chain rule, and we can work even more problems now that also have logs in them. So just the basic log rule, and there's a proof of this in our textbook that just involves rewriting the log as an exponential and doing an implicit derivative. It's really pretty simple. It just requires you to remember how to rewrite a log as an exponential. But the derivative for natural log of x, so this is the most simple case where what we have inside of our log is just a simple single linear x. The derivative with respect to x for natural log of x is 1 over x. So this is specifically for natural log, and it's when the only thing inside is an x. If we put something else inside of that natural log, then we have to treat it like a chain rule. So the derivative, and actually let me go down to the next line because I'm going to write this out in a couple of steps. So if we put something else inside, and we say we want the derivative for the natural log of some function of x, we're going to still remember that anytime we want to take the derivative of a log, what basically happens here is if you're taking the derivative of a log, whatever is inside the log goes into the denominator of a fraction. That's the basic rule for a log. Whatever is inside of the log goes into the denominator of a fraction. That's how we take the derivatives for logs. So to start this problem down here, whatever is inside of the log, we need to put into the denominator of a fraction. That's how the derivative of a log starts. But because this is technically a composite function, we have to do the chain rule. So we also have to multiply by the derivative of what's inside. So the inside stuff is the f of x. So we also have to multiply by f prime of x. So we can simplify this and say, Well, this is really just f prime in the top and regular f in the bottom. And we could just go straight to there. We could say anytime we're taking the derivative of a log, for whatever's inside, its derivative goes in the top, and then the original goes in the bottom. And then that same thing would hold true here for x. The derivative goes in the top, because the derivative for x is 1, and then the original goes in the bottom. X went in the bottom. So for f of x, its derivative went in the top, and then the original went in the bottom. So anytime we see a log, that tells us start a fraction. Anytime we see a log and we want to do a derivative, that tells us start a fraction. Whatever's inside goes into the denominator, and then its derivative goes into the numerator. So that's the basics for doing the derivative of a natural log. Now, some of these problems can get pretty tricky, so it's also helpful to remember some properties of logs, because if you can simplify that log ahead of time, it can make the derivative a lot easier. So these are not calculus properties, these are algebra properties of logs, so you may remember them once you see them. Anytime you are taking the log, and this is not just natural log, this applies to any type of log, but anytime you're taking the log of a product, so inside of your log there's multiplication, you're actually allowed to separate that into two separate logs with addition in between, which is going to be really helpful for us in calculus, because when there's addition in between, we can take their derivatives separately. But when there's multiplication in between, we can't. We have to do the product rule. So if m and n were actually both functions of x, we would have to do a product rule there. But if we remembered this property of logs and we separated them first, we could avoid the product rule. So this could be really helpful for us to just apply that algebra rule really quickly and make that derivative a lot easier for us. So there's another rule that applies for division that can help us avoid a quotient rule. If we had natural log of p over q, we could separate them with subtraction and say this is natural log of our numerator minus natural log of our denominator. And again, if p and q both had x's, we would have to perform a quotient rule in there. But if we separate them with subtraction, we know that with derivatives, once they're separated into two separate terms, we don't have to do any special rules anymore. We can take their derivatives individually. So that would help us to avoid having to do a quotient rule if we could apply that, that algebra rule for our logs first. And then there is a third property that might be helpful with our logs. And this would help us to avoid having to do kind of multiple embedded chain rules. And that is when we are taking the log of something that has a power. So natural log of a to the b. So if a had a bunch of x's in it, or some function of x, and then it was also raised to the b power. So it's not the entire natural log of a that's raised to the b power, it's just a that's raised to the b power. We would have to have an extra set of parentheses in front of the natural log if it was the entire thing raised to the b power. If this was the case, we would have to do two embedded chain rules to do this derivative, but there's a property of logs that say we could actually bring that b out front and treat it like a coefficient. And remember, with derivatives, coefficients just get carried down to the next step in our derivative. We don't have to do anything special with them. So if b is just a number, we really just have to carry it along to our answer and not do anything special with it. If b is a power, then we would have to do power rule as the first step in a chain rule, and then move into the next most interior function, which is probably the log, and then do whatever rule for the log is, and then move inside once more, which is the a, or it would be multiple embedded chain rules, and we wouldn't want to do that if we didn't have to. So anytime that we could use these properties of logs to simplify the logs, it's going to make our derivatives much, much simpler, because the right-hand side of these equations are going to be much easier to take the derivatives of for us. So let's try a few here. And these aren't necessarily going to contain only logs. We still need to remember all of our other derivatives that we've learned as well. And then also what derivatives are used for. Now we're going to learn a lot more in the next chapter about what derivatives are used for. What we've learned so far mostly is for slopes of tangent lines and velocity and things like that. But in chapter 4 we'll learn a lot more. So don't forget about applications as well, and look out for those keywords that in case the directions don't specifically say find derivative, we have those other keywords that also mean derivative. So we'll try a couple really quick, and then we'll look at what we need to do if it's not a natural log, if it is some other type of log, which really there's just one extra little thing we need to throw into our answer. So what if we were asked to find, so the directions here to calculate each derivative. And we'll start off pretty easy. We just want the derivative for natural log of 5x. So any time you see a derivative for a log, you need to start a fraction. And then whatever is inside, that's the only thing you need the log for. The derivative of log means start a fraction. Now whatever is inside is going to go into the bottom, and then its derivative is going to go into the top. So the derivative for 5x is 5. And a lot of times this is going to simplify, because the derivative in the original, a lot of times they're going to have something in common. They might have a coefficient in common, which is the case here. So our numerator and denominator have a 5 in common, which really this just simplifies down to 1 over x. So it's pretty simple. Now it's not always going to simplify down to 1 over x. In the next one, we want the derivative for the natural log of x squared minus 3x. Anytime you're asked for the derivative of a natural log, you're going to start a fraction. Whatever's inside the log is going to go in your denominator. And then its derivative is going to go in the numerator. So x squared minus 3x is just a polynomial. We just find its derivative by doing the power rule on each piece. So the derivative for x squared is 2x, and then we see a minus sign, and the derivative for 3x is 3. And you should check to make sure that does not simplify. We do have a polynomial in the top, polynomial in the bottom. If it's going to simplify, you're going to have to factor and cancel a common factor, but 2x minus 3 does not factor. 2x and 3 do not have any common factor, so there's not going to be anything you can do there. So that's our derivative, 2x minus 3 over x squared minus 3x. The next derivative we want is for x cubed times natural log of x. Now, one thing I have said in the past is when you read these problems, it's good to read them out loud and pay careful attention to the math words that you use when you read them, because that will be a clue as to what rules you need to use. So I'm going to read this one more time. The derivative of x cubed times natural log of x. Times means we need to use the product rule. So we've got x cubed as one of our functions, and we have natural log of x as another function. So we are multiplying two functions of x. We've got to use the product rule. So we're going to start with the derivative of the first one. The derivative for x cubed is 3x squared. And we're going to multiply that by the original of the second one. And then remember, product rule has a plus. And then do original of the first times derivative of the second. Now that's just our simple, plain old standard natural log of x. Its derivative is 1 over x. And I'm not going to leave it like that because these two terms here can be multiplied together and simplified. So this really is 3x squared natural log of x plus, well, 1 over x is like an x to the negative 1, or you can think of it as x cubed over x. Either way, when we combine the powers for those factors with the same base, we get x squared. And that's our derivative. And we're going to look at one more here, and then we're going to go on and talk about what to do when we see some logs and exponentials that have different bases. Because so far, we've only dealt with the exponential with the base of e, and natural log is log base e. So far everything has had base e, but really we can do exponentials and logarithms with any base. So one more quick example first, and we are going to do the derivative for natural log of, let's say, x plus 1 over x minus 1. We want to take the derivative of the natural log of x plus 1 over x minus 1. So we've got a couple different things going on here, and we need to decide where to start. I don't see multiplication. What I see is I see parentheses with a function of x on the inside, and then another operation on the outside. What this is going to be is a chain rule. There's an inside and there's an outside. When I get to the point where I need the derivative of the inside, now the inside itself is a fraction. So when I get to the point where I need the derivative of the inside, I'll have to do my quotient rule. But don't worry about that yet, because we don't do the derivative of the inside yet. So when we do chain rule, we start with the derivative for the outside part. So the derivative for a log says make a fraction. When we do the derivative for a log, we make a fraction and we take what's inside and we put it in the bottom. And then we take its derivative and put it in the top. Now to take the derivative of this stuff, we're going to have to do the quotient rule, because I've got a fraction with x's in the top and x's in the bottom. So quotient rule says start with the derivative of the top. So the derivative of x plus 1 is just 1, and multiply it by the original bottom, and then minus and flip-flop. Original top, derivative of the bottom, all over the bottom squared. Now this looks really ugly, but take it just one step at a time, and you won't be too overwhelmed. Just look for one place to start simplifying. There's not much to do there in the very bottom where we have x plus 1 over x minus 1, so just leave that alone. I am going to start right here. I'm going to start simplifying there, and I'm going to leave everything else alone. Don't try to do too much at once. So first of all, multiplying by 1 does nothing. So really what we have is x minus 1 minus x plus 1 all over x minus 1 squared. And that whole thing is divided by x plus 1 over x minus 1. And now I can distribute that minus and see if I can combine some like terms there. Leave everything else alone. So this is x minus 1 minus x minus 1 over x minus 1 squared all over x plus 1 over x minus 1. Now those x's are going to cancel. And we really just have a negative 2 up there. So the top is written pretty simple now. And the bottom really, there's not much you can do to simplify it. But we don't want to leave it like this. This is a complex fraction. So the last thing we could do to fix this complex fraction is instead of dividing by a fraction, we will flip and multiply. So we've got our top fraction of negative 2 over x minus 1 squared. Instead of dividing by this one, we will flip and multiply. So times x minus 1 over x plus 1. And we've got a common factor in the top and the bottom. We've got an x minus 1 here. Now there's 2 of them down here, so we can get rid of one of them by canceling that one. And what we're finally left with is just a negative 2 in the top. And then we still have one more x minus 1, and we have the x plus 1. Now this one is pretty complicated. So you might want to look back over everything that we did. The most important thing is not to get too overwhelmed with the simplifying. Pick one place to start and leave everything else alone. And usually start in the most complicated spot. Usually start where you see where the most simplifying can be done. And just leave everything else alone until you have that one spot as simplified as it could be. And then pick another spot or pick somewhere else to go to. Don't try to do too much in one step. And don't try to worry about wasting paper. There's no such thing as wasting paper in calculus. You need lots and lots of paper. So this one is a tricky one. So what if we're asked for derivatives of logs and exponentials, but it's not base e? There's actually a rule that we learn in algebra class that's going to help us out quite a bit here. And it's called the change of base formula. Now, as people get newer and newer calculators, they don't need this change of base formula as much, but you may have still seen it. Now, I'm only going to use a version of the change of base formula that's going to be helpful for us here in this situation. But technically, the change of base formula is much more general. For us, what we want to do is use the change of base formula to take a log that's written in a different base and change it to a natural log, because we know how to do derivatives of natural logs now. So if we're given a log that's in a different base and we're asked to take the derivative, what we can actually do before we take the derivative, we can use our change of base formula and we can rewrite log base a of x. Now, a could be anything. I'm not doing the derivative yet. I'm just applying algebra rules and rewriting log base a of x. So right now, this is just algebra. No derivatives. Log base a of x, according to the change of base formula, can be written as natural log of x over natural log of a. So now that we have it rewritten as a natural log, if we try to take the derivative, natural log of a is just a number. So technically, dividing by natural log of a is the same as multiplying by 1 over natural log of a. And that's really just a coefficient. 1 over natural log of a has just a number value. It's just a coefficient. And the function of x that we're trying to take the derivative of is this piece. It's natural log of x. The 1 over ln of a, that's just going to follow our coefficient rules for derivatives, and it's just going to be carried on to the next step. So to do this derivative, this guy just gets carried along, 1 over ln of a, and this piece is what we're going to actually do the derivative of. The derivative for natural log of x is 1 over x. We typically, if we're going to put these back together in one fraction, want to put the x in the front so it doesn't accidentally look like it's inside of that natural log. So it's 1 over x times natural log of a. So if you look back and see how this differs from our basic derivative for natural log, the only thing different, back at the top, we said the derivative for just a basic natural log was 1 over x. The derivative for natural log of x is 1 over x. The derivative for a log with another base, is still going to be 1 over x, but then we're also going to put natural log of the base into our denominator. That's the only difference. So if we write this out a little bit more compactly, the derivative for log base a of x is 1 over x ln of a. So we're still putting the inside stuff into the denominator, and we're still putting its derivative into the numerator. The only extra piece is when we have this different type of base, we're including natural log of the base in the denominator. That's the only extra thing we're doing. And then if this ends up being a composite function, the derivative in the top might not be a 1, it might be something different. So this also could say the derivative for log base a for f of x. So anytime you see the derivative of a log, you're going to start a fraction. There's technically 3 things we need to do here. Anytime you do the derivative of a log, whatever's inside goes in the bottom. Its derivative goes in the top. And because this is not a natural log, this is log base a, we also have to put natural log of a in the bottom. So always check the base on your log. If it's not natural log, then you're going to do natural log of your base in the bottom. So we'll just do one of these real quick to show you. How we do this derivative is not any different than how we did the natural logs. The only thing new is the inclusion of this natural log of the base piece. The other 2 parts are exactly the same. So we're going to take the derivative of log base 5 of the cubed root of x squared plus 4. Now, at first glance, this one looks pretty complicated. It looks like it's going to be a double composite function. So we've got log with something inside, and that thing inside is a composite function. So it's like a function inside of a function inside of a function. But don't forget your properties of logs. We can rewrite this and save ourselves a lot of time. So remember how you can rewrite cubed root. Anytime we can rewrite something as a power, if we can rewrite the entire function inside of our log or the entire expression inside of our log as a power, that power can come out front as a coefficient. So we really can rewrite this as the derivative for log base 5 of x squared plus 4 to the 1/3. Cubed root is the same as a 1/3 power. And when you are raising something to a power inside of a log, that power can come out front of the log. And now it's a coefficient, and when we do derivatives, coefficients just get carried on to the next step. So now it's the derivative. So I haven't done any derivatives yet. This is all just algebra. Of 1/3 log base 5 of x squared plus 4. We just saved ourselves one of those chain rules.
Mom?
So now all we have to deal with is the rule for logs and carry the 1/3 to our answer. So anytime you see a derivative of a log, you're going to start a fraction. So I'm just going to carry this 1/3 to my answer. I'm going to start a fraction because I'm doing a derivative of a log. Whatever is inside the log goes in the bottom. Its derivative goes in the top. The derivative for x squared plus 4 is 2x. And because this is not a natural log, it's log base 5, we also have to put natural log of 5 in the bottom. So I'm going to clean this up just a tiny bit and write it all in one fraction. We've got 2x over 3 x squared plus 4 natural log of 5. Now the order that you write those three factors in the bottom end really does not matter as long as all three of them are there. So by remembering that that cubed root is a 1/3 power and powers can get pulled out front, it saved us actually a lot of work. It saved us an extra chain rule and then a lot of extra algebra simplification later after the chain rule. So there's an example of how we would deal with a derivative for a log with a different base. Really everything stayed the same. The only thing that changed was the inclusion of that natural log of 5 in the denominator. Everything else we would have done exactly the same if this was a natural log. Everything else would have been exactly the same. So the last little bit here is what to do with exponential functions that have different bases. And now that we see what logs do with other bases, it'll be pretty easy to look at kind of the same scenario with the exponentials. So with logs, with the other bases, we divide by natural log of the base. Since logs and exponentials are inverse functions, that means all of their operations are exactly opposite. So in the log, if we divide by natural log of the base, in exponentials, what we do is we multiply by natural log of the base, is the only thing different that we need to do. So remember, anytime we take the derivative of e, it's itself. And that's actually true for any exponential, even if it's not base e. The derivative for any exponential is always going to contain itself. And sometimes, if the exponent is not a plain old x, we need to do a chain rule for that exponent, multiply by the derivative of the exponent. If it's any other base, the derivative is still itself. So let's say it's a. The derivative for an exponential is still always going to be itself. Now with logs, we divide by the derivative, or we divide by the natural log of the base. And we saw why with that change of base formula. In the change of base formula, we end up dividing by natural log of the base. We do natural log of x in the top, natural log of a in the bottom, and that's how natural log of base gets into the bottom. So natural logs and exponentials, logs and exponentials are inverse functions, so all their operations are opposites. So what we change here is instead of dividing by log of the base, we multiply by log of the base. So the derivative for any exponential is still going to be itself, but if it's not base e, we also have to include log of the base, and it gets multiplied. And if that exponent is anything but just a plain old x, we still treat it like a chain rule. So the derivative for a to the f of x would have 3 pieces to it. The derivative for any exponential is always itself. We've got to do chain rule because the exponent is not just a plain old x, it's a function of x, so we also have to multiply by the derivative of the exponent. And our base is not an e, so we also have to multiply by the derivative of the base. So that derivative has 3 pieces. So there's several things to keep in mind when we do this. So we'll look at 2 of these really quick. The first one, we want the derivative for 9 to the x squared power. The derivative of 9 to the x squared power. So this is an exponential function because we have a variable in the exponent. That's what makes it an exponential function. The base is a number and the exponent is a variable. So the derivative for any exponential function always contains itself. And then because our exponent is not just a single simple linear x, we also have to do the chain rule. We have to multiply by the derivative of the exponent. Our exponent is x squared, and the derivative for x squared is 2x. And because this exponential is not base e, it's base 9, we have to multiply by the natural log of 9. That's our answer. And there's nothing we can do to simplify it. One more really quick. We want the derivative for x squared times 2 to the x. Now these look very, very similar, and it looks like there should be something you could do to simplify this, but there's not. One is a power function or a polynomial function, x squared. We would do the power rule for that derivative. 2 to the x is an exponential function because our variable is in the exponent. The derivative for that one is completely different, and they're being multiplied. X squared times 2 to the x. We're multiplying 2 different things that have x's. We're going to have to do the product rule. So our first function is x squared, and our second function is 2 to the x. And we have to do product rule. So remember, x squared we're doing power rule on. 2 to the x is an exponential function. So we start with the derivative of the first function, and the derivative for x squared is 2x. And we multiply that by the original of the second function, which is 2 to the x. Product rule has a plus, and then we flip-flop the original of the first function, and then we need the derivative of the second function. Now our second function is an exponential function. Exponential functions always contain themselves. Now this one, its exponent is just a simple single linear x, so we don't have to do a chain rule. The derivative for x is just 1. If you want to, you can write that. It won't hurt us. We'll just end up getting rid of it here in a minute. The derivative of your exponent is just 1. But then we also, since it's not base e, we also have to include natural log of the base. Now, how far you go in simplifying this is really up to the individual problem directions. Right now, we're really just more concerned with being able to do the derivatives. So there's not a whole lot we're going to do to clean this one up. But we do have 2 x times 2 to the x plus x squared times 2 to the x. We certainly don't need to write times 1 and then natural log of 2. We need all that stuff in there. There's a couple things you can do with some factoring. We've got two pieces here at the front that have a base of 2. It is possible to put those together. Both terms have a 2 to the x we could factor out, and an x we could factor out. There's some different things you could do. It all depends on what the directions are telling you to do in terms of simplifying. But right now we're just concerned with being able to get the derivative, follow all the derivative rules correctly. So really that's all we're concerned with right now. So that is the log rule in a nutshell, the natural log rule, and then also how to extend our exponentials and logarithms to other bases as well.